Space is just another name for size. To say something has space is to say it has dimensions that can be measured. For example, matter is defined as anything that has mass and takes up space. I don't know if size matters, but certainly matter has size, that is space. We can think of space as having three dimensions: height, width, and depth. We can easily measure each dimension with a ruler. Here's a question that will boggle your mind. Will the same object have the same measure of size regardless of its position or the position of the person doing the measuring? For that matter, will the size of the ruler always be the same regardless of perspective? As it turns out, the answer to each of these questions is no. Scientists have proven that the length of an object decreases when it is moving at high speeds. The shortening of distance at high speeds is referred to as space or length contraction. Let's look at an imaginary example of length contraction. Imagine you're at an air show to see the latest jet travel at a speed close to the speed of light. That I know of, no plane can currently come close to the speed of light. But like I said, this is an imaginary example. Furthermore, let's say you have the ability to measure the length of the jet as it passes by. As the jet passes by the first time, you clock its speed at 1,000 kilometers per hour. Let's say you could actually measure the length of the jet as it passes by. When the jet travels at 1,000 kilometers per hour, you measure its length as 10 meters. With the next pass, the jet is traveling at a speed close to the speed of light. Would you measure its length to be 10 meters? As it turns out, the length of the jet would measure shorter than 10 meters. Objects decrease in size in the same direction they are moving. In other words, length is relative to the state of motion of the object and the observer. Now, it's important to note that the pilot would measure the plane to be 10 meters as she is traveling at the same speed of the plane. From the pilot's perspective, nothing changes. So once again, length is relative to the state of motion of the object and the observer. We don't notice length contraction in our everyday life, as nothing we see comes anywhere close to the speed of light. It's important to note that the speed of light is constant regardless of its source and the position of the observer. The speed of light is always c, which is 299,792 kilometers per second. The speed of light does not follow the rules of what we call classical relativity, which explains how velocities are different depending on the relative position of the observer. This apparent inconsistency of light speed with relativity begs the question: how can light have a constant velocity regardless of the observer's perspective? As it turns out, length contraction will help us answer this question. Imagine you observe a spaceship traveling at close to the speed of light. Let's say this ship shoots a laser of light. How fast is the laser of light traveling? Well, you might expect the speed of the laser to be greater than 299,792 kilometers per second, as the laser is being fired from an already fast-moving ship. That would not be the case, however. As the speed of light is not relative to the source of the light, you would measure the velocity of the laser to be 299,792 kilometers per second, the speed of light. To understand how the speed of light is constant, we need to examine the components of speed. Speed is simply the measure of distance traveled over time. The formula for speed is speed equals distance divided by time. Therefore, speed is directly proportional to distance traveled. Albert Einstein, one of the greatest physicists of all time, proposed that for observers to agree on the constant speed of light, they may have to disagree on the components of speed, that is, distance and time. In other words, maybe distance and time change with speed. Let's reconsider the laser shot from the fast-moving spaceship. As speed is directly proportional to distance, and distance shortens at high speeds, the speed of light remains unchanged. In other words, length is relative to speed, and the greater the speed, the more length is contracted. As it turns out, both time and distance shorten with increased speed. The slowing of time at high speeds is referred to as time dilation. Time dilation, in addition to length contraction, fully account for the constant speed of light. In summary, the size of an object decreases in the same direction it moves. Space contraction refers to the shortening of length at high speeds. Space contraction is negligible at everyday speeds from our perspective. At speeds approaching the speed of light, however, space contraction becomes more pronounced. Space contraction is relative to the state of motion of the observer. An observer moving along with the measured object would notice no decrease in length. Only an observer in a different frame of reference, for example stationary, would observe space contraction. Time dilation, or shortening of time, happens at high speeds as well. The combination of time dilation and space contraction fully account for the constant speed of light, regardless of the state of motion of the light source or the observer.